Okay, so I think it doesn't make too much sense to actually write down the solutions of the exercises. What I can do is just make some scan of the sketch of the solutions and provide it to the organizers who will provide it to you, something like that.
Is it fine if you put it on a website, or should we send it by mail to everyone?
By mail, because it will not be pretty. But I think that makes more sense, because otherwise we'll be too slow. And then we can cover some different types of exercises. In the sense that I prefer not to come back now to the exercise of yesterday and just continue with the ones from today. So let me write the tasks for you. But some of them will include, it's on the middle one, yeah. But some of them will include, again, a bit more explanation on the board. For example, for the last one, I want to discuss this active versus passive transformation, and this will take me a bit of time. Okay, the first exercise is about a replica manifold. So consider the sphere with theta is 0 pi, your interval A. So at phi is 0 in spherical coordinates. The task is to write the metric, well, first for the sphere, which should be all right. And then with minimal adjustment, write the metric of the n-sheeted cover of the sphere. So n-sheeted along this interval A that I explained. So, okay, roughly, this is your sphere. Theta is 0 to pi at phi. Let's say phi 0 is in this point. This is your interval, so this is the slit along which you would make an n-fold replicated version of this. So this is the problem about the replica manifold. Then the second one is about the Schwarzschild. So I gave you the definition in the past lecture. I don't know how familiar you are with the Schwarzschild, but the Schwarzschild you'll encounter often, well, depending on which field you are in. But there's something called the Schwarzschild action, for example, in the context of JT gravity and 2D, 1D holography. So the Schwarzschild is around in many places. So let me give you some properties that are useful to know. So the Schwarzschild is defined, let me repeat it. So this is not an exercise yet, this is just me listing some properties that I think are useful to know. One is the inverse, which is, I think it was correct on the board, but if it's not, this is the correct version. So how the Schwarzschild of z of zeta is related to the Schwarzschild of zeta of z, okay? So there's a minus sign coming in here. And then a second property that is useful is the chain rule. for a function which is a function after a function. So it's a chain rule for the Schwarzian derivative. You can maybe this notation is a bit more useful for that. So where I'm using the notation for the Schwarzian f of z to z is Schwarzian f of z. Okay. Okay, the exercise you can do on this is basically a mathematical syntax exercise. I assume that most of you have your laptop with it and that most of you have Mathematica on the laptop, right? Or no, not right? Not correct? Which part is not correct? So, but then this is homework, okay? So so the point is, you don't want to do this operation manually. You want just to define a function in Mathematica that it gives you the Schwarzian for any given function. So define a function, so you can call it Schwarzian. So if you know mathematical language as a function of f, this is an underscore, z underscore, which gives you as an output the Schwarzian. So to write it, you can use module. And if you don't know what that is, somehow Mathematica help is not very good to search. But instead what you do is you just Google whatever you want to search in the Mathematica thing, and you add Mathematica to your Google search. So you Google module Mathematica. And then you will find how to use it. And then once you have this, you can use it to calculate, for example, the Schwarzian that we needed in class. To check that it gives you the same answer, okay? Then a second thing that you can check for the Schwarzian is that it vanishes for this special class of conformal transformations in 2 dimensions, which are the global conformal transformations. So once you've written your module, you can apply it to any function of this form, az plus b over cz plus d, and you will find that it's 0. So what that means is that in the stress tensor transformation rule, this under global conformal transformation, that second part will not be there. This anomalous Schwarzian transformation part will not be there. Okay, and the third exercise will be about passive versus active transformations. Before I write the actual exercise, let me spend a few more words on the difference between those things. Okay, so like I said in class, the difference really is about how you interpret a coordinate transformation. X to x prime is x plus psi. Okay. So the first one, and the passive one, is the simpler one, where if you have an observer that measures this point P, let's say, to be in X, in the position X, then the passive interpretation of this coordinate transformation is that there's an O prime who measures this point to be an X prime, okay? So the change X prime of X is really in the change of the frame of reference, okay? This is the passive picture. And then the active picture is, okay, if you had an O and some point labeled by coordinates X, then the active picture is that you actually push forward this point. Okay, I'm just imagining a random X prime of X now, okay? So that X prime is now here. So you've actually pushed your point to someplace else. But then, subsequently, you find another frame. So let's call it O bar. Who measures this point to be in X bar. Yeah, no. It measures this point to be in X prime barred. That's right. And I've chosen this particular O bar such that this X bar prime is actually equal to X again. So this is by choice of this O bar. So that effectively what I've done in the active transformation. What's happening? Ah, sorry, that's me with the mic. Apologies. Is X prime to X. Sorry. Okay, so this is the passive versus the active picture. So a passive field transformation will be denoted as phi prime of X prime, and an active one as phi prime of X, precisely because effectively you've not changed X. Okay, but really what's behind that is the mechanism that is sketched there, okay? So, for example, the metric, as I said, this one is the easiest to remember because ds squared is invariant, and that allows you to remember how the metric transforms passively, just under a change of frame of reference. Okay, and so, as I mentioned, the trick to find the active version of the statement is to just effectively change x and x prime. And this is the part that I want to explain why it's true, based on understanding the mechanism there. Okay. So here I just apply this trick without really knowing why I'm allowed to apply this trick. So probably best if I start a new board for this one. So let's understand what's happening there on the right-hand side in this active picture, okay? So a coordinate system O will see a point P0 with coordinates x mu. Step one of the procedure there is that we push forward this point to an x prime, where x prime is the value of the coordinates of this point as measured by O. Okay. So everything on this line will be as measured by an observer O. So we push forward the point P0 to P with now coordinates x prime mu is x mu plus psi mu. Okay. So I'm leaving some space to add some things later. Now we introduce this new coordinate system O bar. Which is designed to have the property that the new point P is measured at x again. Okay, so what you have to do for that is change of coordinates. Well, I can write it here. You have to do change of coordinates. X to x bar is x minus psi, so that if you go this way, P is measured with coordinates x prime bar is equal to x prime minus psi is equal to x. I can't help that this is a bit tricky to follow. It's probably better if you just do it on paper. So, and P0 is now at a coordinate x bar, which is x minus psi. Okay.
Is there an extra increase on the active metric transformation out there? There's a g mu x prime equals.
Oh, sorry. Yeah. Yeah, you have to tell me if I write mistakes. Thank you. Okay. So now, if you're interested in a field at these locations, these in these four cases, then here you would have a point, a field in the point P0, which is labeled by x according to the observer O. Here, that field would be g mu in x plus psi, so in x prime. But then when you push it forward to here, you will have a g mu nu measured by O bar, so barred g mu nu in x prime bar, which is equal to g bar mu nu in x. And this is the one we're interested in finding. And all we need is understanding first this step of pushing forward the points, and then just applying the passive coordinate transformation rule for the metric that we do understand, which is the one that just expresses invariance of ds squared. Okay, and the combination of that will give us the correct G bar, namely okay, so here all I'm doing is using, so there's no stick, but I'm using the...
There's a stick left to me.
Aha, sorry, thanks. So I'm using this transformation rule applied to this passive transformation from x prime to x prime bar. So everywhere where I have an x there, I have an x prime. Apologies for the mu nus and the alpha betas being switched. It would have helped if I didn't do that. Sorry. But, okay, well, no, I won't change it. And all the x primes are x prime bars, okay? Is that true? Yes. So here I'm just applying the rule that we understand, the passive coordinate transformation rule for the metric transformation to the coordinate transformation x prime to x prime bar. And then I make the choice of O bar being precisely the frame that measures this point to now be at its coordinates x. So you make the choice that x prime bar is x. So this line is just a choice of coordinate system O bar. So having done that, I have G bar mu nu of x is G alpha beta of x prime, dx prime, dx, dx prime, dx. And that is all I needed to show. So it means that my active field transformation rule that I've written there upstairs with the simple trick of just swapping x and x prime is indeed giving me the new metric actively transformed in x. Okay, so I'm just saying this right-hand side here is the same as the right-hand side on the right of the top board. So this explains this swapping x with x prime trick. That effectively, this is the way to obtain the active transformation law from the passive transformation law. Right, so the exercise you can do about that. All right, here is to make a sketch of the three frames of reference O, O prime, and O bar that came into play in this argument for P0 at x and P at x plus a, where a is now a constant. Here, my xi, this was just a general statement for xi, some function of x. But for the case of a translation where a is constant, and you can choose A to be slightly smaller than X. For this case, you can make a sketch of where these frames are, and that might help. So these are the three. Okay, sorry, I went back to the middle board. Ah, you didn't. Thanks. So these are the three exercises, so take it away.
Please repeat the first one.
The first exercise? So the exercise is to consider the sphere, as I drew here, in spherical coordinates, so r, theta, phi. Well, basically theta, phi. Your r is constant. First up is to write the metric for the sphere. And then consider this interval, which is the one that I tried to draw here. It's the interval theta equals 0 to theta equal pi at phi is 0. I've chosen my phi is 0 to be here. And once you have the metric for the sphere, there's a minimal adjustment that you can do to write the metric of the n-sheeted cover of that sphere along this interval. And so there's two pieces, two tips I can give. One is that it's a minimal adjustment, and it's a minimal adjustment that involves the parameter n. Okay. And second is that we know the structure or the characteristics of this n-sheeted cover, in that it will have conical singularities at these two special points. And from the discussion of how these conical singularities arise, you can try to cook up the metric for the n-sheeted cover. I could also just give you the metric and then have you check that it has the conical singularities in the right place, but it helps to think about it for a bit first. I turn on my mic so that everyone hears this one. You write down the metric for the sphere in theta phi coordinates. You understand why that metric is smooth everywhere and does not have conical singularities at these special points. Theta is 0 and theta is pi. In the way that we discussed in class, that if the angle around those points has the right periodicity, there will not be conical singularity. So if you understand why that metric is smooth at theta is 0 and theta is pi, you'll be pushed in the right direction to understand how to change that metric, but keeping the same coordinates, keeping theta and phi as your coordinates that now will span a different metric, that by changing one term in your sphere metric with factor n somewhere will have the effect of introducing conical singularities where they weren't before. Let me write the answer for the first exercise. So basically, your replica manifold will be n spheres that you connect, okay, along this slit, which is A. So let's start with the metric for the sphere. Which is this. The point is to remember, so R is a constant radius. The point is to remember that this is not enough information to explain to me what the sphere is. You also have to add the range of the coordinates. And so the range of the coordinates is theta to pi, theta from 0 to pi, phi from 0 to 2 pi, and then you identify. And phi from 0 to 2 pi is the right angle for there not to be any conical singularities when you circle the point theta is 0 and theta is pi. Okay. The n-sheeted cover okay, you can either write as a change in the range of phi and keep the same metric, or you can insert that information in how you write the metric and keep the range of phi. Okay, those are two options that you can do. Let me write the second one. So the second one is this, where theta still runs from 0 to pi, but phi now runs, and phi runs from 0 to 2 pi. But phi running from 0 to 2 pi is not the range that gives you a smooth metric. It's the one that gives you a conical axis. Okay. Right. The point is just include coordinate ranges when you write a metric, especially if you're dealing with conical singularities. Otherwise, you don't give me enough information. Okay. That's exercise number 1. Exercise number 2. I don't know if anyone tried. I don't see too many laptops, but I can write you the syntax. Well, yeah, or there's no slides, presentation mode, probably.
Just see
That would be quicker, I think, because otherwise I have to write.
Can you connect that? Or
Yeah.
do you need HTML?
HDMI, but that looks like HDMI, no?
No.
Wait, let me try.
Maybe meanwhile, how can I see that it's not smooth anymore?
Ah, well, you need phi from 0 to 2 pi n for the smooth solution. So in the same way that you need phi from 0 to 2 pi for this to be smooth, you need n times phi to have a range 2 pi to be smooth in this line.
In what sense is this not smooth though? If you choose n to do something else.
Okay, wait, you need n phi from 0 to 2 pi or phi from 0 to 2 pi over n for a smooth solution. Well, in the same sense that here, if, okay, this is your sphere, and we know the sphere is smooth for your azimuthal angle to go 2 pi around this point. So anything, any identification that is not 2 pi will not be smooth. That's just this argument for the plane, and you cut out some part and identify these things.
But how do you, is there something you can compute that blows up at the...
Yes, the Ricci scalar.
Okay.
It will have a delta function in the origin.
But if you, as you said before, you could calculate the... Okay, I don't know if you think about that.
Yeah, but that being said, I don't think these Mathematica packages, for example, will pick up on that because it's a delta function. So it's,
Okay, so
yeah.
because you said you could also write a metric without the n in the metric, but just with a different range for...
Yeah. I didn't write it because if I need to think about it, but this one is probably the right one, right? This would be the conical excess, I think.
I think so, yeah. So
It just, I didn't want to write a wrong thing. Yeah.
if you write it like that and then calculate the Ricci scalar, right, and any of the curvature tensors that you calculate are only local. So if you have two metrics that in whatever coordinates you choose, if the metrics look the same,
Yeah.
but you have a different range, you won't see that in the Ricci tensor.
No, that's why something like an RGTC package on Mathematica will not pick up on it. But really, your Ricci scalar will have a delta function.
Okay, so is the problem that you're not specifying what the metric is at the point? Okay, maybe this is the way to put it. So like, you're not actually including the singular point in your metric when you write it down, but when you have the correct range, you can smoothly continue it over that. You can smoothly continue the metric to that point. But if you choose n not equal to 1, then you can't smoothly continue the metric. Is that kind of the idea?
I don't know. I don't know how to say it in those words. The point is just this picture, and that does produce a delta function singularity in your Ricci scalar, but
how would you show that?
well, with pen and paper probably, as in that the package won't help you, but.
Okay, but what I don't see how you would find that, because you always calculate the Ricci scalar locally, right? If you just calculate it in terms of the way you've written the metric down,
Yeah.
you'll get the same thing no matter what n is. So I don't see where the delta function will come out of the calculation.
I think part of the difficulties comes from like it's not like a normal manifold anymore. You can't have like a local covering that will give these coordinates, so it doesn't have like a normal tangent space. So I think you can't use the same technology or the same arguments.
So
I don't know exactly what happens.
yeah. So this is what I was trying to say about that you can't smoothly continue the metric to the singular point. Like I can kind of see. Maybe this delta function is a different way of expressing it. I'm not sure.
Well, yeah, it's a singularity in the metric. Yeah. Yeah, sorry, I didn't know where the sound came from. Yeah.
This interval at phi equals 0. So you said at the exercise that you cut the sphere at the semicircle at phi equals 0.
Yeah.
And then you glue the sphere together. But is there a reason for this? Or could it be any interval? Or can we see?
That was just a setup that our interval is stated from 0 to pi. Yeah, that's just a setup. Yeah. I think I should stop though.
Yeah, I mean, it depends if you still want to show your package.
Right. Well, this is the answer for how to write the Schwarzschild. So this is the answer for the second exercise, which is just a mathematical syntax exercise. So you use module. Module takes on here some functions that you internally define, but you don't need any internally defined functions, so that's why it's empty. And then you just write this definition, so such and such derivatives of f. And here you check in the second line that this is actually producing the right derivative. And you can check in the next line that it vanishes for this general global transformation. And this part, the next line is the particular z of zeta that we needed in class. And you plug it in, and it gives you the answer that we use in class, okay? Just there's a non-zero chance that you will work with Schwarzschilds, and then it's more convenient to calculate them with this line than on paper. Okay, so this is the answers to 1 and 2, and then the answer to 3. If you need it, let me know, and then I add it to the sketches of the exercise solutions. But now I have to hand it over to Nabil.